Okay, so chapter 6 deals with the subject of thermochemistry. We're going to start thermochemistry just by looking at a simple reaction. It's the combustion of hydrogen gas in the presence of oxygen gas, which produces water vapor. As you can see, that water has the subscript G next to it, which denotes it's a gas, so that would be steam. And, this is just a simple combustion reaction. If you've ever heard of the Hindenburg, this is the reaction that happened there. The hydrogen gas that was in the Zeppelin or the airship, whatever you want to call it, burned in the presence of oxygen and created a lot of steam, but it also released a lot of heat. Okay, it released a lot of heat energy. And what we notice when we look at this reaction is that chemical reactions involve bond breaking and bond forming. By now, you know how to draw the Lewis structure of hydrogen. So we're starting it with two molecules of hydrogen, and we're also starting it with a molecule of oxygen. And these are the Lewis structures for hydrogen and oxygen. And then we end up forming two molecules of water, and we can draw the Lewis structures for those. There's one water molecule. Here's another water molecule. And hopefully it's clear to you that we're breaking bonds, right? We're breaking two bonds between the two hydrogen bonds in the two hydrogen molecules, and we're also breaking the double bond between the two oxygens. How do I know that? Because when I look at the structure of water, there are no hydrogen bonds in there, and there are no oxygen bonds in there, right? I'm forming four new bonds, and they're all oxygen hydrogen bonds. I have 1, 2, and 3, and 4. And there's an energy change associated with this reaction. Like I just told you, that this reaction releases a lot of heat, energy, and so energy changes accompany chemical reactions. The energy of the reactants and the product differs, and that's why we get energy released during this particular reaction. Now, thermochemistry, which is the subject of this chapter, is the study of the heat that's evolved, as in the case of this reaction shown in this slide, or absorbed in chemical reactions. We're going to look at a lot of chemical reactions in this chapter, and we're going to discuss the amount of heat that's either evolved or absorbed in those reactions. Well, let's keep going. Before we get into that, let's define a little bit more about energy. And energy is nothing more than the capacity to do work. In fact, that's a definition that you should know. If you think about, yourself in terms of your personal energy levels, if you wake up in the morning and say, I don't have any energy, what does it mean? It means you don't want to work. You don't feel like doing any work because you're low energy. Now, there are several types of energy that you need to be aware of. Radiant energy, that's the energy that comes from the sun. It is the Earth's primary energy source. It's what helps crops grow and keeps our planet warm. The next is thermal energy, which is the energy associated with the random motion of atoms and molecules. So the more an atom or a molecule is moving, the more thermal energy it has. Chemical energy, of course, we're going to be talking about that. It's the energy that's stored within the bonds of chemical substances. If you go back to the last slide and you look at that hydrogen bond or the oxygen bond, there's some kind of energy associated with those bonds. And there's energy associated with the oxygen hydrogen bonds in the water molecules. Nuclear energy, that's mostly discussed in general chemistry too, but that's the energy stored within the collections of neutrons and protons in the nucleus of an atom. And then finally, potential energy. If you've ever studied physics, I'm sure you've discussed potential energy, which is the energy available by virtue of an object's position, by where it is. Okay, so those are some different forms of energy. Now, if we think about energy changes in chemical reactions, we need to discuss heat. And heat is the transfer of thermal energy between two bodies that are at different temperatures. And I want you all to know that when we discuss the flow of heat always flows, okay, so heat always flows from hot to cold. It never goes in the reverse direction. Heat is always going to flow from a hot body to a cold body. And temperature, we talk about temperature all the time in our everyday life. We say, I measure the temperature. What's the temperature of this? Or take my temperature. I'm not feeling well, maybe. Temperature is a measure of thermal energy. And what was thermal energy? It was the energy associated with the random motion of atoms and molecules. And so you've got to understand that temperature does not equal thermal energy. These are not the same thing. What do I mean? Well, if let's say you had, 1 cup of water, it's at 100 degrees Celsius. So that's boiling water, but you've only got 1 cup of it, maybe, a coffee cup or one standard cup full of water. You could measure the temperature of that water and say it's 100 degrees. And then you could say, well, there's some thermal energy associated with that. Well, if let's say we have a swimming pool full of water, and that water is at, let's say, 60 degrees Celsius, which would be really hot for a swimming pool. But anyhow, overall, since there's so much more water in a swimming pool, even though the temperature is lower, we would say that overall the swimming pool has more thermal energy, right? Because there are many, many more molecules in there. And so overall, the amount of thermal energy in a swimming pool at 60 degrees Celsius would be greater than in, say, a cup of water that is at 100 degrees Celsius. So again, temperature and thermal energy are not meaning the exact same thing. Now, what exactly is thermochemistry? The subject of this chapter, chapter 6 in our textbook. Thermochemistry is the study of heat change in chemical reactions. Now, a lot of times when you teach chemistry, there's always some student in the class, not you guys, of course, who's always saying, when do we get to the explosions? Well, generally speaking, as chemists, we aren't looking to blow things up in the lab. We're trying to keep our students safe. But if you think about an explosion, that's a chemical reaction, just like, whether it's the hydrogen combusting in the Hindenburg, or whether it's trinitrotoluene, which is one of the components of dynamite, whether it's that, exploding, you can see that there's definitely some heat exchange involved in those chemical reactions. And so when we're doing chemical reactions, the actual vessel or place where we're doing the chemical reaction, we have a special name for that, and we call it the system. The system is the specific part of the entire universe that is of interest in the study. So the reaction that we're looking at is going to be performed in a system. And there's 3 types of systems that you need to be aware of in general chemistry: an open system, a closed system, and an isolated system. So what it's showing here in this figure is that what is exchanged in these 3 different types of systems? Well, if we do a reaction in an open vessel, now these are all different, these are called Florence flasks. If we're dealing with an open flask like that, so the top is open and you can see that there's no insulating material on it, well, what does that mean? It means if you do a reaction in that vessel, it's going to be able to exchange both mass as, let's say, water vapor, or steam, let's say, or some other gas that's produced can come out of the top, right? So it can exchange mass, and it can also exchange energy in the form of heat. Maybe it's releasing heat or maybe it's absorbing heat, but either way, an open system can exchange both mass and energy with the universe. A closed system has a stopper in the top, and so the system is unable to exchange mass with the universe, but it can't exchange energy, right? Because there's no insulating material, and so it's still able to exchange heat, energy, with the surroundings or the universe. And finally, in an isolated system, this is where we have not only the vessel closed off to the universe, but it's also insulated. And so it can exchange neither mass nor energy. So 3 types of systems that you need to be aware of moving forward in this class. Let's talk about what are called exothermic and endothermic processes. We've spoken about reactions that release energy into the surroundings, and we've spoken about reactions that absorb energy into the surroundings. And exothermic and endothermic, those are words that we use to qualify those 2 types of processes. And so, an exothermic process is any process that gives off heat, releases heat, transfers thermal energy from the system to the surroundings. Some examples are the combustion of hydrogen, right? You can just Google the Hindenburg and watch the video on YouTube, and you can watch the explosion and everything that took place in Lakehurst, New Jersey in 1937. Or here's another example, which is water in the vapor phase. We call that steam, right? And then we have water in the liquid phase, and we simply call that water. Well, if you've ever been burned by steam before, let's say you have a kettle of water boiling on the stove, or maybe you have a plug-in kettle or something. If you've ever reached across that kettle by accident and the steam has touched your skin, what happens when the steam touches your skin? It goes from the gaseous phase to the liquid phase, right? It condenses on your skin, but what else does it do? It releases a whole big old pile of energy. And that is why steam causes such severe burns on skin, okay? Because not only do we get the change, but we get the release of energy. And so the first example here, the combustion of hydrogen, that's a chemical change, right? That's an actual chemical change where we break bonds and we form bonds. This example here, this is a physical change, where the water is just changing phase, going from a gas to a liquid. Now, in an endothermic process, this is any process in which heat has to be supplied or put into the system from the surroundings. Here are a couple of examples. The first one is a chemical reaction. If we take mercury 2 oxide or mercuric oxide, that's this molecule here, it's a solid at room temperature. If we heat that up, in other words, we supply energy to it, we can break apart the bonds in mercuric oxide and produce mercury, the liquid, metal, and oxygen. But we have to supply that energy. And so this is an endothermic, right? Endo kind of makes me think of the word in, right? You're putting the energy in. Conversely, if we look at a physical change, and this is nothing more than the melting of ice, okay? Solid water, I'll tell you that we call that ice. You probably knew that. So if we take ice and we convert it to water, we know that that takes energy. You could use the exact same kind of example. If you take an ice cube and you put it on your skin, it feels cold. Why? Because the ice is actually taking heat from your body, and it's using that heat. It's transferring that thermal energy from your body into the ice cube, okay, into the crystal lattice of the ice in order to melt it into form water. So a phase change, physical process. So exothermic processes and endothermic processes. One thing I just want to point out before we continue on is a little bit of, kind of wording here I noticed when I was lecturing, is that here I use the word surroundings, okay? You see that I have the word surroundings here. And then if we back up a slide, I talked about the universe, okay? Now, if you think about the universe, the whole entire universe, I mean, if you do a reaction down here on planet Earth, if you do any of those reactions that were on the next slide here on planet Earth, it's probably not going to affect what's happening, in another solar system somewhere, okay? It's probably not going to affect the entire universe a whole lot. And so another word or another descriptor that we use for the universe is the surroundings, because we're really only concerned with the immediate environment that surrounds the system where the chemical reaction or the physical process is taking place. Let's talk about endothermic and exothermic processes a little bit more and look at this schematic here. Now, these are two different processes. These are two chemical changes. The first one in A shows the combustion of hydrogen gas, right? So this is the combustion of H2 in the presence of oxygen, of course, and we end up producing water. Well, as we discussed, this is an exothermic reaction. It gives off energy to the surrounding, to the universe. So what does that tell us? It tells us that the energy of the products is lower than the energy of the reactants or the starting materials. Now, where does that energy go? It goes into the surroundings. Over here, you can see the opposite. You see an endothermic process, where we take that mercury 2 oxide or mercuric oxide. In order for it to be converted into liquid mercury and oxygen, it has to absorb heat from the surroundings. And this is what we call an endothermic reaction. Okay? And so you need to understand an exothermic reaction. And when we look at an endothermic reaction, the products are actually higher in energy than the starting material. Okay, so exothermic and endothermic processes. What's thermodynamics? Okay, I'm sure you've all heard of the laws of thermodynamics, even if you've never studied them before. You may have heard of them, somewhere in your travels. Well, thermodynamics is a bigger topic than thermochemistry. It's the scientific study of the interconversion of heat and other kinds of energy, right? And we can think of all kinds of, examples. If we go back to the slide or a few slides ago, when we talked about different types of energy, you think about, the radiant energy from the sun that causes plants to grow, and then there's chemical energy stored in the bonds in plants, and then we digest the food. And what do? We take the energy that's in the chemical bonds in the food that we eat, and we convert that into thermal energy in our bodies, and we convert it into kinetic energy when we move. So, what's another example? You think about the chemical energy that's stored in the bonds in something like gasoline. You put it in your car and you burn it, and you turn it into kinetic energy, right? It also is converted into thermal energy. The engine heats up. So, we could sit here all night and everybody could come up with an example of that. Okay, so thermodynamics, again, is that scientific study of the interconversion of heat and these other kinds of energy. And before we can truly understand and, discuss all the ins and outs of thermodynamics, we have to discuss what are called state functions. State functions are properties that are determined by the state of a system, and it doesn't matter how that condition was achieved. Okay, how it got there is irrelevant. All that matters is the state of the state. Okay, the state of the system and nothing else. 4 state functions that you're going to be concerned with in Chemistry 111 are energy, pressure, temperature, and volume. Now, the symbol that's used in our textbook for energy is delta U. If you're the kind of person who likes to look around the internet or look at other textbooks or look at examples that are worked out on the internet, delta U stands for the change. That's what the delta stands for. So this would be change in energy. And if you look at other textbooks, sometimes they use delta E. Okay, so sometimes, energy can be delta E some of the time, but again, our textbook uses delta U for energy. Now, if we want to calculate a change in energy, pressure, volume, or temperature, all we have to do is to use any one of these formulas here, right? If I want to calculate, let's say, the change in volume, I take the final volume and I subtract the initial volume. Same thing for temperature. If I want to find out the change in temperature, I take the final temperature, subtract the initial temperature, right? And the same thing applies for energy. Here's a practical example. You see, there's a mountain here, this beautiful mountain. I don't think it's Pikes Peak, but anyhow, let's say, imagine yourself at the top of this mountain. I'm the king of the world, right? Anyhow, if you hiked up the mountain following this path in yellow, or let's say somebody else took, a longer path, like this path here in red. They're longer paths. But when you and your friend get up here at the top, you both have the same amount of potential energy. Right? There's no difference in the amount of potential energy that you both have. It would be both calculated. The difference in energy is take where you started and subtract where you ended up, and that's the change in energy, right? Or I guess a better way to say it would be, you both have the same amount of potential energy because you're at the same height. I think that would probably be a better way of explaining it. Anyhow, give me a thumbs up if you follow me on that. State function, just determined by the state of the system. The pathway that you took to get there doesn't matter whatsoever. It's totally irrelevant. And if you're wondering, are we going to look at things that aren't state functions? Oh, absolutely we will. Absolutely we will. Okay? But I just want you to be aware of what a state function is, and you kind of have to be in order for us to keep moving. Okay? Well, let's look at my second slide that deals with the topic of thermodynamics, and it covers the first law of thermodynamics. There are 3 laws of thermodynamics, but tonight we're just going to discuss the first law of thermodynamics, which says energy can be converted from one form to another, right? We can convert radiant energy into kinetic energy, and radiant energy into thermal energy, and chemical energy into kinetic energy. Anyhow, it can be converted from one form to another, but you can't create it and you can't destroy it. Okay? Can't create energy and you can't destroy energy. Let me think about that. Well, if that's true, okay, another way, or two different ways, I guess, really, of writing the first law of thermodynamics would be this. The change in energy for a system, my chemical reaction, right? The system is my reaction. And then the change in energy for my surroundings, the environment where I'm doing the reaction, if I add the changes in energy for my system and surroundings, overall it should equal zero. What do you mean by that? Well, what I mean by that is, let's say you're burning some propane, okay? This is propane, C3H8 is propane. If you're burning some propane, right, you generate energy, okay? It's going to produce some energy. But that chemical energy gets lost by the combustion of that propane, okay? Some of it's going to go into the chemical bonds of carbon dioxide and water, but we know that some of that energy is also going to go into the surroundings, okay? And so the energy that's lost by combustion in that system has to go into the surroundings. And another way of writing that would be this, would be to rearrange this formula that I have the little blue mark by and say the change in energy for the system is equal to the negative sign of the change in energy of the surroundings. Okay, so heat energy lost by the system is going to be equal to the heat energy gained by the surroundings. That's for an exothermic chemical reaction. For an endothermic reaction, you would say the chemical energy gained by the system is equal to the chemical energy, the energy lost by the surroundings. Okay? And so before we can keep going, I want you to give me a thumbs up if you just follow me on, kind of the concept between these two formulas here, that the change in energy for the system is going to be equal to the minus sign or the opposite of the change in energy for the surroundings. All right. It's not meant to be, going fast or anything. I just wanted to kind of enjoy talking about thermodynamics this evening. All right, good. There we go. Well, let's look at another way to write the first law of thermodynamics in terms of the change in energy for the system. And this one might not be intuitive, so you'll kind of have to bear with me while I explain it to you. Okay? And again, we saw that a way to write the first law was that the change, and I'll just put it up here so that it's in your head. So the change in energy for the system is equal to the negative of the change in energy for the surroundings. Okay, so that was one way to write the first law, but here's another form. Okay, and the other form is this. The change in energy is equal to Q plus W. What's Q plus W? Okay, well, Q is the heat exchange between the system and the surroundings. Okay, well, that seems reasonable. So Q, the letter Q, I know it might not be intuitive, but Q stands for heat. And then W stands for work. That one's a little bit more intuitive. The work done on or by the system. And now heat, we just discussed heat, but how would we define work? Well, this is a formula that you need to be aware of, that work is equal to the negative of pressure times volume when a gas expands against a constant external pressure. Now, if anybody here has studied physics before, I'm sure you've heard the formula work is equal to force times distance. Okay, and if you haven't, well, I'll just tell you. In physics, they always say work is equal to force times distance. Okay, and we're going to explain as to why work in chemistry, we don't define it as force times distance. We define it as negative P times delta V, but there's a reason why, and you'll see how that relates to F times D in a second. Now, before we can get into a practice problem, which we're going to do in a couple slides, that deals with this formula, or these formulae, delta U is equal to Q plus W, and work is equal to negative P times delta V, we have to clarify the sign conventions for work and heat. I'm sure there's somebody who's hearing me lecture and saying, what's this minus sign all about? What's that for? Well, let's think about it. If a chemical reaction produces a gas, okay, let's say you do a reaction and it produces a whole bunch of gas. Well, that gas is going to do some work against the surroundings, right? The gas is going to expand into the surroundings. And so it's doing some work against that surroundings, which are at a constant pressure, because most chemical reactions are done at constant pressure. Well, if the work is done by the system on the surroundings, it gets a negative sign. Now, all kinds of students have all kinds of ways of, rationalizing this. But the way that I think about it is if the work is doing, sorry, if the system is doing work on the surroundings, I say like the work is leaving the system. Okay, so it gets a negative sign. Right? The opposite, if work is being done by the system, on the system rather, by the surroundings, we give it a positive sign. Now, what about heat? Q, right? Because remember, work, okay, this is W, and heat, this is our Q, okay? If heat is absorbed by the system from the surroundings, that's an endothermic process, right? It's taking the heat in, right? So you think, okay, well, I'm adding heat to the system, so it's a positive sign. And if heat is being absorbed by the surroundings from the system, so the system is releasing heat into the surroundings or the environment, that's an exothermic process. I think, well, it's negative, right? It's like your bank account. You're losing money. It's a negative sign, right? It's going down. Okay. So you have to be fully aware of those sign conventions for work and heat in order to be able to properly apply this formula right here. All right. And actually, in order for you to understand the sign that you'll get when you use this formula. Well, let's look at work is equal to negative P times delta V first, okay? And I want to tie that in with work is equal to force times distance for all my, students who have studied physics maybe in the past or maybe in the present. Well, if work is equal to force times distance, and this is more of the physics way of looking at it, and in chemistry, we think, well, work done by a system is equal to negative the pressure that of the environment where the reaction is being done times delta V. Well, what's pressure? Right? Pressure is equal to force per unit area. How could I define area? Area is a distance squared, right? So that's where I get this, and that's where this term comes from. So P times V is equal to force over distance squared. Volume is going to be equal to a distance cubed. Right? If you have a distance and you cube it, you can find the volume. And so what happens is if we take pressure times volume, we have force over distance squared times distance cubed. What happens is d squared in the denominator here cancels and the cube cancels, and we get force times distance, F times d. So that explains that. Now, what about the sign? Well, we said that when work is done by the system on the surroundings, it gets a negative sign, okay? When work is done by the system on the surroundings, we get a negative sign. And that's what's being shown here in this scenario right here, okay? So this is a scenario. It says, let's say you're doing a reaction. There's some kind of reaction taking place in here, and that reaction involves the expansion of a gas, right? What's happening is you can see the volume of the gas here is getting bigger. And so overall, there's a change in the volume. And we know that since volume is a state function, we can say that the change in volume is equal to the final volume minus the initial volume. Well, if this is the final volume, right, this is VF, and this is VI over here, you can clearly see that VF is bigger than VI, and so delta V is going to be a positive number. Another way of saying that is that it's going to be greater than 0, right? The change in volume is going to be greater than 0. Now, atmospheric pressure, or the pressure of the environment that you're going to be doing the reaction in, is always going to be positive. The only time you wouldn't have a negative pressure. The only time you'd have no pressure is if you were in a vacuum. You'd have a pressure of 0. So again, most of the time we're going to be doing reactions at atmospheric pressure, and so our pressure is a positive number. If we take minus P, right, which is a positive number, times delta V, which is a positive number, right, when we're dealing with this scenario where a gas is expanding, we get that our work, which is equal to maybe I should put work of the system, just to clarify. The work of the system, which again is equal to negative P times delta V, is going to be a number less than 0. So the work done by the system will be a negative number, which is less than 0. Let's go back here and check. When work is done by the system on the surroundings, right? This is the scenario, let's say, where a gas expands, the sign of work is going to be negative. I love it when a plan comes together. All right. Now, it might be a knee-jerk reaction to say, well, pressure and volume are both state functions. And so work must be a state function. But in fact, work is not a state function. We cannot simply subtract W initial from W final to calculate delta W. Can't do that at all. Okay? If you think about, people getting the same amount of work done, for example, let's say one person pushes a bunch of boxes that weigh hundreds of pounds across the floor. Well, they're going to move the boxes to a new position. Let's say another person puts the boxes on a dolly, or some kind of cart, and pushes them along on wheels. Well, the boxes are getting to the same place, but the two people did very different amounts of work. And so work is not a state function. We can't simply take the initial and final states in order to calculate a change in work. With all that in mind, let's take a look at our first practice problem of the evening. A certain gas expands in volume from 2 liters to 6 liters. So this is an expansion. It's getting bigger from 2 liters to 6 liters at a constant pressure. Calculate the work done by the gas if it expands against a vacuum or against the constant pressure of 1.2 atmospheres. Well, in order for us to do this question, we need to have our formula, which is work, W, is equal to negative P times delta V. I think the first thing we should do here is calculate delta V, because we know delta V is equal to the final volume minus the initial volume. And the final volume is 6.0 liters. The initial volume was 2.0 liters. And so we get a delta V, which is equal to 4.0 liters, like that. Okay, now that we've got that, we can work out these two different scenarios. Now, if this gas is expanding against a vacuum, what's our pressure going to be? If we're going against a vacuum, there's no pressure at all. Okay, so in that case, we'd have a pressure equal to 0 atmospheres, like that. Well, if we use our formula, W is equal to negative P times delta V, I'm sure you can all work the math out for this one in your head, that it's negative times 0 atmospheres multiplied by 4.0 liters. Well, work is going to be equal to 0 atmospheres liters, which we normally write, and this is just kind of a convention, we write it as liters atmospheres. Now you might be wondering, what are the units of liter atmospheres? The units of liter atmospheres are actually energy units, and I'll get to that in a second. But let's take a look at the second problem first. So we've already solved the first one, that the work is equal to 0. Let's take a look at the second one. If we're expanding that gas against a constant pressure of 1.2 atmospheres, plug some numbers in. Work is equal to negative the pressure times delta V, which is equal to negative 1.2 atmospheres multiplied by 4.0 liters. When we do that, we get that our work is equal to negative 4.8 liter atmospheres. Now, the conversion factor that you're going to need here to convert liter atmospheres into energy units that we're familiar with, which are joules, is this one here. 101.3 joules are in 1 liter atmosphere. So liter atmospheres cancel out, and we end up with the amount of work. We should only have 2 significant figures in our final answer, and we end up with negative 4.9 times 10 to 2 joules. So that's around 490 joules of energy, or joules of energy, yes, as our work. Now, what I want to point out to you, well, first of all, I guess we should write in here that work is also equal to 0 joules. Okay, so OJ or 0 joules. Anyhow, a couple of things. Okay, the first thing is, and I know I've mentioned this many times this evening, but I just want to go over the sign. Okay, we have a negative sign for our work. Okay, well, that makes sense because the gas is expanding against a constant pressure. So it's going to do work against that pressure in order to let that gas expand. Okay, another thing here is that even though the change in volume is the same for both of these scenarios, we end up with different values for our work based off of our pressure. Let's try another example. Example 6.2. The work done when a gas is compressed in a cylinder is 462 joules. So this is work. During the process, there's a heat transfer of 128 joules from the gas to the surroundings. Calculate the change in energy. For this problem, we're going to use this formula. The change in energy is equal to heat plus work. Now, the only problem here is discerning what are the signs going to be for our work and for our heat. Let me ask you guys a question, and let me get it set up for you here. But in the first sentence, it tells us that the work done when a gas is compressed in a cylinder is 462 joules. So is work being done by the system, or is work being done on the system? Keep in mind the gas is the system, right? Is work being done by the system or on the system? By or on, I guess. Yeah, work is being done on the system, right? Because you're compressing that gas. And so our work is going to have a positive sign. It's going to be plus 462 joules. Now, with respect to our heat, it says during the process, there's a heat transfer of 128 joules from the gas, from the system, to the surroundings. So will the sign of my heat, my Q, will that be a positive or negative sign for my 128 joules? If heat is being transferred out of the system into the surroundings. Thanks, Trevor. You're 100% correct. The answer is, Trevor says it's negative. It's going to be negative 128 joules. Look, everybody who's hearing the sound of my voice is capable of adding two things together. It's just a matter of interpreting the problem and knowing whether their signs are positive or negative. And so we have negative 128 joules because heat is being released from the system into the surroundings, plus 462 joules because work is being done on the system by the surroundings. And when we tally all that up, we get a change in energy that's equal to 334 joules. Just like that. The change. All right, give me a thumbs up if you follow me on that one. Our first two problems. Kind of fun problems. Yeah, great. Okay, great. Well, I want to get right into the next subject, which is what is called enthalpy. Enthalpy and how it relates to the first law of thermodynamics. Now, you might be wondering, what the heck is enthalpy? Well, enthalpy is H. Okay, so we use capital letter H to represent enthalpy. I'll put that right here. So capital H. And so enthalpy is what we use to quantify the heat flow into or out of a system in a process that occurs at constant pressure. Okay, so this is very important that you know that enthalpy is used to measure heat flow in a system or a reaction, which is the system, of course, that occurs at constant pressure. Now, enthalpy is defined as this right here. Enthalpy is defined as the change in energy for our system plus pressure volume work, right? The product of pressure times the change in volume. If we go back to this equation here that we looked at the very beginning, the change in energy is equal to heat plus work. This was another way that we rewrote the first law of thermodynamics. Now, if the heat of a reaction that's performed at constant pressure is equal to the change in enthalpy, and if work is equal to negative P delta V that we looked at in the last few slides, then we can rewrite the first law by substituting in those two equations as the change in energy is equal to the change in enthalpy minus P delta V. But most often, when we're looking at reactions that occur at constant pressure, which is in fact most reactions that are done in chemistry, we're more concerned with calculating change in enthalpy, which again is defined as change in energy plus the product of pressure volume work. Here's that definition of enthalpy that I gave you a couple of minutes ago. Enthalpy is used to quantify the heat flow into or out of the system in a process that occurs at constant pressure. I can't stress this enough. You have to know that enthalpy is measured for reactions that are performed at constant pressure. Okay, very, very important. Now you might be wondering, well, how else could I calculate change in enthalpy? We could use this formula right here, that the change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. And so the change in enthalpy is nothing more than the heat given off or absorbed during a chemical reaction that occurs at what? Constant pressure. Here's a couple of scenarios. We looked at endothermic and exothermic reactions earlier on. Now we're going to see how they relate to delta H, the change in enthalpy. If I have an endothermic reaction, here's a reaction. Sorry, this isn't a reaction, this is a physical process, this first one here. But this is an ice cube melting, right? This is just water in the solid phase, so ice. And then we have water. Well, in this case, heat is going to be absorbed by the system, right? You know that you have to have heat in order to melt an ice cube. And we can actually quantify that heat absorbed, that change in enthalpy, which is 6.01 kilojoules per mole. That means for every mole of water, it takes 6.01 kilojoules of heat absorbed in order to melt that ice and convert it into water. If we look at the next example, which shows the combustion of methane. So this is methane gas, which is one of the major components of natural gas. When it combusts or burns in the presence of oxygen gas, it forms carbon dioxide and water, but heat is given off. And we can quantify that change in enthalpy because we're doing the reaction at constant pressure. And that heat that's given off during that reaction at constant pressure happens to be a negative number. It's negative 890.4 kilojoules per mole. And so our change in enthalpy is a negative number. It's less than zero, right? So again, this is an exothermic process. And over here we have an endothermic process. Now you might be asking yourself, how do I know when delta H is going to be negative or positive? There's probably many ways that students kind of rationalize this in their own minds, but if the system is absorbing heat, that's going to be an endothermic reaction, right? It's got to take the heat in. Again, here's that example of the ice melting. 6.01 kilojoules are absorbed for every 1 mole of that ice that melts at 0 degrees Celsius in 1 atmosphere, standard temperature and pressure, right? You remember these? Oops. These are STP, okay? And our delta H is going to be greater than 0, right? If we go back to this equation, delta H is equal to the enthalpy of the products minus the enthalpy of the reactants. Here's another way you can think about it. These are the products up here. These are the reactants down here. If the enthalpy is increasing in this direction, we can clearly see that the products have a higher enthalpy than the reactants. So we have a big number subtracting a small number, so we're going to get a number that's greater than 0. Same rationale applies for an exothermic reaction. Here's that same reaction that we looked at earlier, the combustion of methane in the presence of oxygen. You can see that the enthalpy of the products is lower than the enthalpy of the reactants. We go back to our equation. Delta H is equal to the enthalpy of the products minus the enthalpy of the reactants. We're subtracting a small number, or sorry, we're subtracting, yes, we're taking a big number and we're subtracting it from a smaller number. So we're going to end up with a negative number. And so this is an exothermic reaction. Again, we're going to release 890.4 kilojoules of energy for every 1 mole of methane that's burnt at, this reaction happens to be done at 25 degrees Celsius in 1 atmosphere. All right. Some important things to remember about delta H. What can you do with delta H? How can you manipulate delta H? Well, the first thing that you need to know is that stoichiometric coefficients always refer to the number of moles of a substance. So since we're dealing with 1 mole of water and, ice and 1 mole of water in this physical process, that means 6.01 kilojoules per 1 mole of water, of ice, and per 1 mole of water. If you reverse a reaction, the sign of delta H is going to swap. It's going to go from positive to negative or negative to positive. Let's look. If we take water and we freeze it, right, we convert it into ice, it's the opposite. We just swapped or reversed this reaction up here. So what are we going to do? We're going to reverse the sign of our delta H to negative 6.01 kilojoules per mole. The last thing is that if you multiply both sides of an equation by a factor of n, which is an integer, whether it's 2, 3, 4, 5, so on and so forth, delta H is going to have to change by the same factor. What's happening here is I'm taking this equation and I'm multiplying it by 2 to give me 2 molecules of ice, or 2 moles of ice rather, give me 2 moles of water. Well, I'm going to have to take my enthalpy value and multiply it by 2. And so the change in enthalpy, sorry, I'm looking at the wrong reaction, aren't I? Oops. Let me just fix it. When I saw the sign, I was like, that's not right, is it? There we go. So, sorry, it's this reaction here that I'm reversing. There we go. Fixed it, okay? So we would take this and we would multiply it by 2 as well, okay? These are some rules that you have to be able to apply in order to be able to manipulate delta H. One more thing I want to show you about delta H before we call it quits for the evening is that when you're looking at all these equations and whether they're physical changes or chemical changes, the physical states, okay, which are what? Solid, liquid, and gas, those of all your reactants and products, those have to be defined, specified in the thermochemical equations. Let me give you a $100 reason as to why. Look at these two physical processes here. We're taking ice, right, and we're melting it. Okay, so this is melting ice. Then we're taking water and we're vaporizing it, right? This is vaporizing water. And they have very different delta H values, right? It takes a lot more heat energy to vaporize water, 1 mole of water, I should say, than it does to melt 1 mole of ice. And so, again, the states of matter are going to be very important as we move forward in this chapter.